Okay, thank you very much, and thank you to the organizers for inviting me. That we're gonna to be here this nice and great conference. So, well, I'm going to talk a little bit about what is listed here, and mainly trying to make some connections between those topics. Okay, let's see if I know how this works. Anyway, doesn't matter. Uh, a brief overview of what I'm going to talk about. Well, first about counting problems in general, what they're needed for, why they're useful, and why people want to study them. Then I will kind of zoom in a little bit on the subject of this talk, which is the constraint satisfaction problems, well, the account inversion. I look at several, not so recent results, but just to kind of lay the background for the future work, which is, I will explain what exact counting means in this sense. And then, if time permits, I'll talk a little bit about the ongoing work, related to so-called modular counting and things like that. So it would be really great if this thing works, but it does. Okay. So, counting problems. Let's start with some kind of simple example. Suppose I have a graph which is a very old, as you can see, computer network, and it's so old that it breaks down all the time. For instance, every link in this network can break down with probability 1/2 at any given point. So, of course, we want to connect. We want to have a connection between two nodes. Say, these two nice personalities. But of course, since things break down, with some probability, the network may get disconnected, right? So, for instance, if we toss a coin for every edge, I remove this edge with probability 1/2, and in this case, they got disconnected. Okay, so what is the probability that these two nodes are connected at any given point? Of course, what we need to do, we need to count. The probability 1/2 is, of course, kind of very special because it means that if we break a link with this probability, what we're actually doing, we are selecting a random subgraph of this graph, right? And therefore, the probability that they're connected is, the number of all subgraphs in the denominator and the number of subgraphs in which S and T are connected in the numerator. So in this case, we do want to count something. Okay. Another example, that will go a little bit further than just such a toy problem. Suppose I have a graph. Well, we know this problem of graph coloring, right? Say, color a graph in 3 colors. I probably have a picture. Say, can I color this graph in 3 colors? Okay, in this case, we cannot because can we or can we not? Anyway, doesn't matter. What I want is a coloring. So in this case, what is the probability that I guess a proper coloring? For instance, for every node, I toss a coin with 3 sides because I have 3 colors, for instance, and I decide which color the nodes are going to be. Say like this. Am I successful? Not quite, right? This one is not proper. Well, again, how do I compute this probability? Well, I need to take the number of all proper colorings divided by the number of all colorings. This one is easy, right? Just for each node, I have 3 options, so I can compute, right? It's 3 to the power of the number of nodes, but this one is a little trickier. Okay. Obviously, this is not how people normally use this kind of counting because it's difficult to decide if there is even a single coloring, right? So how would I count the number of them? What people normally do, they would try to sample a random coloring. Right? And that would work somehow like this. Say, if I take a random coloring, what is the probability this vertex is red? Okay, how do I figure it out? Well, I need to look at all proper colorings and count how many of them this vertex is red. Then I will do for all the colors, and then I toss a coin with the, well, corresponding probability distribution and assign a color. Then I say, okay, this vertex is red. What is the probability this one is blue? And I repeat the process. So this way I can prove in the end that in the end I will get a random coloring, meaning that every coloring appears with the same probability. Why do we want to need this? Well, for several instances. Say, if we want to run some randomized algorithms like Monte Carlo, for instance, right? Well, to compute whatever I want to compute. Say, for instance, nuclear reactors are routinely designed using Monte Carlo algorithms. So there are a lot of randomization involved in those designs. Somehow they still work, which is a surprise. Right? Or, for instance, we want to test our software, and then we need a random instance of our problem to test how it works. Again, well, approaches like that would work. Actually, there is a very tight connection between sampling something and counting this thing. So, generally speaking, if I can count, I can sample. If I can sample, I can count. So, in that sense, counting is very important as well. Okay, well, in those two cases, the counting problem is actually difficult, right? But any easy counting problem, well, for instance, I want to know how many solutions are there for a system of linear equations. Say I have a system of linear equations. It looks somehow like this. Since I want a number, I shouldn't be talking about, I don't know, real numbers or something like this, right? If I have any solution in real numbers, if I have more than one solution in real numbers, I have infinitely many solutions. So that's not interesting. So what normally people do, they say, okay, let's suppose this is over some finite field, right? Some finite numerical field, and then we can count solutions. Why is it easy? Well, if you know a little bit of linear algebra, that's easy to understand. That's because I can find the basis of solutions here, and then, well, I can just use this basis to figure out the number of solutions. So in this case, everything is linear algebra. So some of those problems are difficult. Counting colorings is definitely difficult because, well, finding one is difficult. Deciding if there are non-zero number of coloring is difficult. But say in this case about linear equations, well, that's easy. Okay. Connections to other areas that where people may be interested in something like this is this framework from statistical physics, which is called spin systems. They have been studied like since Boltzmann in more than 100 years, and it works like this. Suppose I have some particles, molecules or something like that. They may have one of the two spins, right? Left or right, or maybe the other way around. Okay, anyway, so one of the two spins. And what we know about that, that if I have a pair of interacting particles, the energy of the interaction depends on the combination of spins. So if they are left-left, they may interact with some energy. If they are left-right, with some other energy, and so on. So generally speaking, for such interacting particles, I would have some kind of a little matrix that says, okay, if they are left-left, they interact with this energy, and so on and so forth. Okay. Why is it important? Well, this is because everything, like the air around us, can be thought of a system of such interacting particles, like, say, air molecules or whatever, right? And, well, we normally assume they form some kind of a graph. Say, for instance, in crystals, that's this crystallite lattice. And, well, physicists call such graphs spin systems. Okay, so all these molecules in the air, in the crystal, or wherever, will interact, and the energy of the interaction, well, depends on this matrix. So what do we want to know? Well, we may want to know, well, several different things. For instance, if we leave our system alone, what kind of state is it going to be in? Right, this is all ground state, right? The state of the lowest energy. Or if I warm up, I don't know, a crystal, at what point it's going to melt? The phase transition. And so on. And all of that can be actually computed through those, through this framework and so-called partition functions of this of those systems. Okay. So first of all, let's talk about configuration of a spin system. Well, we have those interacting particles, and we say, well, this one spin left, that one spin right, left, right, right, left, etc., etc. That's a configuration of our system. If we have this configuration, what we can do, we can compute the energy of the system. Right? So that's this value h that depends on the configuration, and basically compute it using that little matrix I showed in the previous slide. For every pair of interacting particles, I take the corresponding value from the matrix and sum them up. Okay. So the probability that the system is in a certain configuration, well, is this. Well, don't pay attention to this exponent. What is important is this, that this exponent contains the number we just defined, and also some parameter, which is the temperature of the system. If we raise this parameter, energy grows in general, right? So the energy of the interaction grows, and so on. What is important here is this z, which is the partition function of the system. Okay? And how we use this partition function? We normally use it somehow like this. Well, there are these threshold values for the partition function, and say if it's greater than some value, our crystal is going to melt, right? Or liquid evaporates, or something like that. So phase transition, right? And obviously it depends on the temperature. The higher the temperature, well, the more likely that our system is in this kind of more liquidy or more gaseous state, right? Again, physicists, what they do normally, they try to given a material, they try to evaluate this partition function depending on the temperature so that they can predict all these phase transitions and things like that. So this is how it's not exactly counting, right? Because we are summing up some things, but nevertheless, we will see that it's very much related to counting. Because a very special case, if this matrix depends on nothing, if the energy of the interaction is the same, that z is basically the number of configurations, sort of admissible configuration in something. So indeed, in that sense, that's how it's related to count, and I will expand on that a little later. Actually, there are more connections here than just that. Again, if we want physics, nothing is exact, right? We want to approximate things, and well, that's a vast area of research. If you look at literature on all the spin system, partition functions, glass models, and stuff like this. This is just like tens of thousands of papers. It's very, very big area. Okay. If we talk about computational complexity, in computational complexity, we divide these problems into complexity classes. Okay? So what is the proper class for partition function, for counting problems? Well, I hope everybody is familiar with at least two complexity classes. Well, P, problem solvable in polynomial time, and NP, problems for which solutions can be verified in polynomial time. Right, so this class sharp P for counting problems, is some kind of a descendant or derivative of this class NP. Okay? So how does it work? What are problems in NP? Well, these are those problems, right, for which we can check a solution. So there is a solution that is some kind of, well, they call it a certificate, which is short enough, polynomial in size, it's short enough, and we can check if this is a solution in polynomial time. Okay. So there is a polynomial such that for every instance input for our problem, we can find, we can guess a certificate which is short enough, and then check that this is a correct certificate. So the counting problem in this case is just, okay, well, how many proper certificates are there? This is what we count. If you like Turing machines, for instance, they say, well, non-deterministic Turing machines, this is the number of accepting paths of indeterministic Turing machine. So this is what we count. But that's kind of very abstract, right? Certificates, what the hell are certificates, and so on and so forth. So for us, it's normally going to be just the number of solutions. And for specifically for the constraint satisfaction problem, solutions is something very specific. Well, we can kind of define it very well, and there would be no confusion like this. What is certificate or anything like this? Everything will be much nicer. Okay, so given an instance, we want to find the number of valid certificates. That's the general understanding of the counting problems. Obviously, it very much depends on the choice of certificates. Usually, there is huge freedom to do that. But again, in specific problems like the CSP, well, it's very clear what it's going to be. So we shouldn't worry about this abstract nonsense in this case. Okay. So the class *P is the class of all counting problems like this. Okay. All right. So how are we going to count? Well, I will list like 3 models which we use to count. Well, first of all, it's exact counting. Just give me the number, exact number, like 2,524. Just exact number. Obviously, this is going to be difficult in many cases. Like, find the number of, I don't know, colorings or something like that. Okay. But nevertheless, we will start with that. We would like to understand the complexity of this. Okay. More practical approach is approximate counting. Find the number of solutions within some multiplicative error. Okay. So for instance, the standard model of approximate algorithms in this case is so-called FPRESS. So I need to decode this. It's a fully polynomial randomized approximation scheme. A bit mouthful. But anyway, so that's an algorithm that is efficient, given an instance, and allowed error. So we may say, okay, count our colorings with an error at most 30%, plus minus 30%, something like that. So allowed error. It finds a solution which is within a multiplicative error of 1 plus epsilon. Right? So if, for instance, there are 1,000 solutions, it's okay, and epsilon is 0.3, then it's okay if it says 1,300 or it says it's 750. Right? That would be within an error. But note the kind of very special properties that I can say which error I allow. Right? I want 30%, okay, here is a solution within 30%. I want 10%, here is a solution within 10%. Well, where is the catch? Right? Why not say 0 and just get an exact number? The catch is, of course, that the running time, the efficiency of the algorithm depends on the error. The lower the error, the longer it runs. So if I say, okay, let epsilon be 0, it will run forever. Okay, so I don't want that, so okay. I will not be talking about that much because that's a really separate area, and well, it has its own problems and approaches and all these things. That's a really separate area. Okay, what I will say a few words about in the end, hopefully I will have time, is so-called modular counting, which is I want to find the number of solutions modulo some integer. For instance, the parity. Do I have even number of solutions or odd number of solutions? Well, you can imagine that it may be easy a little bit, right? Because, say, for instance, having even number of solutions in terms of parity, right? An even number of solutions or 0 number of solutions is the same thing, so maybe it's going to be a little bit easier. Okay? And we will actually see that sometimes it's much easier than exact count. Okay, so the next character in the story is a constraint satisfaction problem. Okay, I will give a bunch of examples, explain what it is, and what we count in this case. Okay, so I will start with a construction that is known as graph homomorphisms. Okay, well, suppose, all right, formal definition. I think I have a picture. That's probably easier. Okay, I have a pair of graphs. Well, you may recognize the graph from the previous slides. And well, I have another graph. Right? So graph G, graph H. Now what I want to map every vertex of the first graph into a vertex of the second graph in such a way that an edge is mapped into an edge. So for instance, in this case, I have all possible edges here. This means so the only restriction in this case is that I cannot map an edge here into the same vertex because I don't have loops. Right? Well, if you think about it, what is going on in this case, I need to assign every vertex a color in such a way that adjacent vertices don't get the same color. That's a coloring problem. So for instance, in this case, for this specific graph, which is the click KK, for instance, K5 in this case, what I'm looking for is just 5 colorings of an input graph. But obviously, I can put something different here, like a different graph or something like this. Well, we'll see several examples like that. And well, in those cases, I will be looking at something different. Okay, again, we will see a few examples a bit later. Okay? So formalizing things a little bit, the problem K coloring, right? Now the instance is I'm given a graph. I want to find, well, counting problem now. I want to find how many colorings are there, right? So something like that. And well, I can restate it in the form how many homomorphisms from G to the, well, K click are there. So in this case, homomorphisms are exactly the same as colorings. So counting colorings is the same as counting homomorphisms. Okay. Well, why should I restrict myself with a click? I can take some other graph, and then I will get something different. Okay. Well, another observation, why should I restrict myself with graphs? Well, graphs are kind of convenient, nice, etc., etc. But overall, something very restricted. What is a graph? By definition, a graph is a set of vertices and one binary symmetric relation on those vertices, the edge relation, right? The edge relation. So why only one? Why symmetric? Why binary? I can generalize that and say, okay, well, a relational structure, which is a generalization of graphs, is a set. But then I allow as many relations as I want of any arity I want, and so on and so forth. So if you're not very comfortable with something like that, well, in what follows, you can think about graphs. That's pretty similar, well, kind of more complicated, of course, but nevertheless, the overall idea is the same. So it's just a set and some relations. We'll see examples. Okay. So for instance, 3-SAT. Well, the 3-SAT problem, again, we have this formula, right? Logic formula, first propositional logic formula with clauses, which are just disjunctions of variables. And we want to satisfy them all at the same time. We can formalize it as a relational structure as follows. So 0, 1 are the possible values, right? 0 and 1, true, false, right? Then I have 8 possible types of clauses. So it may be X or Y or Z. It may be X or Y or not Z, X or not Y or Z, and so on and so forth. 8 possibilities. Okay, I list them all. And each of those relations is a kernel relation that exactly satisfies that clause. So for instance, 0, 0, 0 corresponds to X or Y or Z. It's satisfied by everything except 0, 0, 0. False, false, false. And so on and so forth. Okay. Well, I say that two structures are similar if the names and arities of relations are the same. So, for instance, I may say, okay, now I come up with a different structure that is on 0, 1, 2, but it has, again, 8 ternary relations. That would be a similar structure. Any two graphs are similar, right? Because every graph is a set and one binary symmetric relation, right? Binary relation. So any two graphs are similar. Okay. So a homomorphism in that case would be generalization of graph homomorphisms, a mapping that maps vertices to vertices or elements to elements and relations to relations. So for instance, a relation, any tuple from R000 in the first structure is mapped to a tuple from R000 in the second structure. So for graphs, it would be H goes to an H. Right? Any tuple pair from this one binary relation goes to a pair from that one binary relation, H to an H. So here we have more types of edges and they're more complicated. But overall, this is it. No more difference than that. Okay? So what is the constraint satisfaction problem? Well, constraint satisfaction problem looks like this. For instance, for 3CNF or for 3SAT, it looks like that. Say I am given an instance. I want to find a solution of this instance. So I want to find the assignment of zeros and ones that satisfies my formula. In more general case, I may have something like some relations, and I want to find an assignment that makes them all true. That's basically what constraint satisfaction is. Or, okay, so the counting is, of course, the counting CSP is, of course, just the counting of the number of satisfying assignments. So again, well, that's a counting problem. It's those certificates and blah, blah, blah. But in this case, certificates are just solutions. Number of assignments that satisfies a logic formula. Number of colorings that are proper, and so on and so forth. Okay? All right. Another way to say what constraint satisfaction is like for graph homomorphism. Given two similar structures, decide if there is a homomorphism from one of them to another. So graph homomorphism is a special case of the CSP. And I can come up with many, many different examples. Like, if I want the counting version, of course, I just need to count the number of homomorphisms. So that's the framework. That is the framework. Okay, examples, a bunch of examples. So how do linear equations fit into the picture? Well, I have a system of linear equations. Find the number of solutions. Find the number of solutions. So in the irregular decision CSP, it would be the question, is it consistent? If there is a solution, in the counting one is, of course, just the number of solutions. How is it related to those, to the CSP? Well, how do equations are related to the CSP? Well, so we will look at every equation as a constraint, right? As a constraint that a relation, right, that consists of all triples, like x1, x5, x7, that satisfy the equation. So what we want an assignment that is good for all of those constraints, that satisfy all the equations. Okay. Clearly, if I just look at the general CSP, two relational structures, two graphs, if there is a homomorphism, I cannot model too much using that. So what we normally do, we would restrict the problem to get something interesting. So since in every time we are given two relational structures, we can say, okay, don't take any relational structure on the left, don't take any relational structure on the right, just structures from some specific classes. So what we get in this case is something like this. Well, this is a letter G, if you can recognize it. Right, well, it's a Gothic font, so that's a very nice and kind of beautiful letter. Well, so this is G, and any guess what this is? H, right? Well, the hints are all over the slide. So this is G, this is H. In this case, I just say, okay, take this one. Well, sorry, that's the input is, well, take the first structure from this class and second structure from this class. For instance, I want to count the number of colorings of, I don't know, 5 colorings of a planar graph. That would be the class of all planar graphs, and that would be just a single structure, which is K5. So that's roughly how restrictions work. And clearly, by doing that, you can get a lot of interesting problems. Again, some examples follow. Okay. Well, sometimes people use notation like this, where star means whatever, anything goes. So we restrict on the left-hand side. Or this, where we say, okay, we only restrict the right-hand side, and here we have whatever goes. Okay. A very special case is when our right-hand side class contains only one structure, and left-hand side is unrestricted. This is where the majority of attention goes. Somehow this is the most interesting case. The most interesting case. The rest are either easy, yeah, or, well, not that interesting. Okay? So I will mostly be talking about CSPs like that. They are sometimes called non-uniform CSPs. It doesn't matter. So, K-coloring is counting CSP to a K-click. Well, we've seen that. H-coloring, H is a graph, counting homomorphisms into a graph. Not necessarily K-click, but some other graph. I don't know. A two-path, or something like that. 3-sat, counting homomorphisms to that structure, 3-sat that we saw before, right? It has 2 elements, 0, 1, and the relations actually encode the possible 3 clauses. A homomorphism in that structure means a satisfying assignment to some logic formula. Okay. Number of linear equations. Well, we need to be careful constructing this structure, but we can do that. And in that case, counting the number of solutions to linear equations is again a counting CSP to that new structure. Okay, what is this? Counting CSP to a graph like that. Well, think about it. This is K2, isn't it? Right? So counting a homomorphisms to K2 is K-coloring. So that would be 2-coloring, which is basically deciding or counting the number of ways we can find a bipartition of the graph, right? Non-zero value will be only for bipartite graphs, and we are counting the number of bipartitions. Okay. This way, we count the number of cuts in the graph. So the number of homomorphisms to that, well, not quite simple graph, but anyway, is the number of cuts. Well, if you think about it, that's a little bit too trivial. Well, it basically says I can map whatever, wherever, right? Everything is connected. But we will see how to fix that problem. Okay? A little bit more. Well, this is an interesting one. This is counting the independent sets in a graph. How so? Where are independent sets? So imagine what is going on. I have a graph on this side, and I am mapping this graph into this thing. Where is the independent set? Of course, whatever I have in my independent set, well, all the vertices are not connected to each other. And if you notice that any 2 vertices that go here must be disconnected. So the preimage with the set of vertices that go here is an independent set. So this is how I count independent sets in the graph. Bipartite independent sets. Independent sets in a bipartite graph. Well, again, if you think about it, the vertices that go here and here form an independent set in a bipartite graph. So again, well, we can kind of simulate a fairly interesting problems this way. Okay. Sorry. Okay. So if we go back to cuts, this one is not very interesting, as we concluded, right? Why? Well, that's because, well, anything goes, so it's kind of trivial. We have a graph, cut it anyway, it's a cut, so why bother? What we may be interested in, and what people are interested in, is, say, finding the number of a maximal cut. Like a cut containing the maximal number of edges. How can we simulate this with a problem like that? Well, we can. But in order to do that, we need to add weights to our structure. So suppose that we like some solutions of our CSP more than others. For instance, we like larger independent sets. We like smaller cuts, whatever. Right? In that case, what we can do is we can add weights to simulate that. For instance, I want to somehow elevate large cuts in my graph. How can I do that? Well, instead of just unweighted graph, I can use an edge-weighted graph, where the edge that corresponds to the cut has higher weight. So I kind of want to map edges into that edge. Right? The more edges I map here, the better for me. Right? I will get a cut of higher weight, which means, well, in this case, translates into more edges in the cut. Okay? Well, if so, I take my graph, right, map it here somehow, right, using this mapping sigma, for instance. Then I can compute the weight of the mapping as follows. For every edge in my graph, such that one of the vertices, one of the ends of the edge is mapped here, and the other vertex is mapped here, I will multiply the result by 2. So I will multiply the weights of images of all edges. Right? If an edge is mapped here, well, I don't care. The weight is 1. It doesn't change anything. But if an edge is mapped here, well, it will add 2, or rather multiply the result by 2. Okay? And now, the weight of G is computed like the sum of all those weights. Now, if you think about it, cuts, well, this is a cut, right? The set of edges that go into this one is a cut. So large cuts will contribute more, relatively speaking, into the sum. And actually, by playing fairly simple tricks, I can kind of elevate those so much that everything else kind of doesn't matter. And I can find the number of maximal cuts. Actually, you can do even better. You can find in the number of cuts of every size by playing like this. Right? Say I can find the sum like this, then I can find the size and the number of maximal cut. I subtract that, I get something else, etc., etc. So well, that works. If you remember something from about half an hour ago, which is a tough call, that should remind us something. That's exactly the partition function. So this is where partition function appears in combinatorics. Right? We know that some of them work in statistical physics, but also in combinatorics. Right? All these weighted cuts, etc., etc. Well, that's more or less what all these spin systems in statistical physics are. So that's some kind of an unlikely marriage of combinatorics and statistical physics. Is right where partition function. Okay? All right. So that's what we get basically. Okay, back to partition functions, just a formal definition. What we have? We have a matrix, say n by n, over some numerical set. It may be real numbers, complex numbers, finite fields, whatever we want. Right? The problem partition function is given a digraph, right? We want to know which one is first, which one is second, which end of an edge is first, which end is second. So we want to find the partition function. Well, for any possible mappings, we compute the weight of the mapping similar to what we did in the weighted cut. And that's exactly what statistical physicists do. Well, they want to evaluate things like that. They have a bunch of models that do exactly this. And that's a big area. I will mention it once more, but not that much. Okay, now we can talk about the complexity of such problems, and probably this is about how much time we have. But anyway, so complexity of what? Obviously, if we are talking about the complexity of the CSP in general, it is hard. It involves three satisfiability, it involves three colorings of graphs, whatever. All the difficult problems are there. Right? So we don't want to talk about that. What we are going to do, we're going to restrict our problems by using those classes of structures and then say, okay, if we restrict it this way, we get an easy problem, and therefore, I don't know, three coloring of planar graphs is easy, right? Because rather five coloring of planar graphs is easy because every planar graph is five colorable and so on and so forth. Okay? So if we introduce just the left-hand side restrictions, do something on planar graphs, right? That normally the complexity of that is related to a parameter that I want to introduce, but it's called tree width of our structures or graphs. And basically it works like this. If this class has a tree width, it has bounded tree widths, like at most 10, for instance, then the problem is easy. If it doesn't have bounded tree width, then the problem is hard. So for instance, planar graphs have unbounded tree width, which means that normally counting problems on planar graphs are as hard as just counting problems in general. So planarity doesn't help that much. Okay? So that's a relevant reference in this case. Well, seen from the other side, meaning seen from the left side. People would look from the right side rather than wrong side. That's the other side. Okay? What about partition functions? For partition functions, things are kind of interesting. Again, so far we are talking about exact counting. So suppose we have a matrix. Remember this rectangular square matrix for partition functions. And suppose it's connected. What it means connected? Well, you can imagine something like this. It means that you cannot kind of split it into, well, separate several rows, several columns in such a way that, say, I have something non-zero here and the rest here and here zero. Right? It cannot be kind of split into blocks. That's what connected means. In this case, partition function is easy to compute if and only if the matrix has rank 1. Which is pretty simple, right? Pretty simple. Otherwise, it's difficult. So in a way, a partition functions, exact counting of partition functions is hard in almost all cases, except for a fairly trivial one. A fairly trivial one. This is why physicists are not that much interested in exact counting. They want to approximate. And approximation works better in at least some cases. So, for instance, counting independent sets is a partition function of such a matrix. Right? Remember the corresponding graph. It's this edge with a loop and without loop in one place. So this is the lack of one loop, and that's the other loop, and this is the edge between them. So it's connected, right? You cannot split it into blocks in any way, but it has rank 2, obviously. Right? So this is hard. You kind of have immediate consequences like this from this general result. But again, that's kind of old one. Okay. All right, so let me cover that. I want to do something similar, but now with relations. How am I going to do things with relations? Look at this relation. It contains 1, 2, 3, 4 triples. So it's a ternary relation. It contains 4 triples. What I'm going to do, I look at the first 2 coordinates. Right? For the first 2 coordinates, I have 3 admissible combinations: 0, 1, 0, 1, 1, 0, 1, 1. Now I count in how many ways I can extend 0, 1. 0, 1 I can extend in 2 ways. 1, 0 I can extend in 1 way. 1, 1 I can extend in 1 way. Okay? And 0, 0 is nowhere here, so it can be extended in 0 ways. That defines a matrix. That defines a matrix. number of extensions of 0, 1, number of extension of 0, 0, of 0, 1, 1, 0, 1, 1. Okay, so that's a sort of a matrix that I construct from a relation. Well, there are also more involved ways to do that, but that's the overall idea. Okay, I will say that my relation is balanced if this matrix has rank 1. Remember, rank 1 corresponds to easy problems, partition function, easy partition function. Okay, so relational structure, if every its relation is balanced, is called balanced, and if I throw into the mix some kind of derivative relations, well, again, doesn't matter what kind of relations these are, I will say that my structure is strongly balanced. Right? So that's the connection to matrices. And strongly balanced, okay, well, it's some kind of derivative relation. So what we know is that, and that's a slightly more recent result, is that I have a relational structure, then my counting CSP is polynomial time, if and only if my relation is strongly balanced. So this rank 1 appears here as well. Otherwise, it's hard. So that was a major result at some point. And okay. All right. Well, this one has been generalized in multiple ways. One of the important ones is adding weights. So, well, you can add like positive integer weights, positive, negative. You can add rational weights, positive rational weights. You can add real weights, positive real weights, negative real weights, complex weights, and so on and so forth. So people have been looking at that for all these combinations, and the most general result is a classification of such counting CSP with all possible complex weights. That's by Jin Tsai and Shi Chen. Well, now fairly recently. Okay, good. So I probably spent just a few minutes talking about modular counting and what is the difference between exact counting, which is now, well, pretty much understood. Again, I haven't talked about. I'm not going to about approximate counting. That's its own ball game. Completely different. There a lot of is understood, a lot is not. A lot of open problems. Modular counting is what we are doing right now. So let me just give you a couple of hints what can possibly go wrong with modular counting and why it may be easier than exact counting. Clearly, exact counting cannot be easier than modular counting. If you can count something exactly, you can then take the just take this number modulo whatever, and that's it. Okay, so counting CSP modulo P, I will normally assume that P is a prime number. It doesn't matter. I have two relational structures. I find the number of homomorphisms, but modulo P. Like modulo 2, the parity, modulo 3, and so on. Okay, if I fix the structure, then this problem is sharp P, modulo P, CSP of H. Well, they belong to class P, which is the count of those certificates modulo P. So look, previous definition stay and add modulo, and somehow now things going automatic. It's probably I need to kind of speed up. This is what it means. So what can possibly go wrong? How difficult is it to count 3 colorings modulo 3? Good. So why is that? 3 colorings are homomorphisms to this graph, of course. Right? So I have my graph, and I count homomorphisms. Okay? Suppose I find one. But then you just notice that if I rename the colors, right, like this, for instance, well, it's also a homomorphism, right? Who cares how you call colors? Which means that every homomorphism here comes with 2 more homomorphisms, 3 total, and I'm counting modulo 3, right? So if I have a homomorphism, then combining this homomorphism with this automorphism of the triangle, automorphism means a homomorphism into itself. What is going on here? And well, doing that once more, well, I again get homomorphisms, and this means that my homomorphism phi contributes 0 modulo 3. So 3 colorings are somehow easy mod 3. That's troubling because, well, clearly things may be more complicated with that. That's a very simple example. So how more complicated can they be? Okay. Say, for instance, instead of a triangle, I use a star. Well, a star also has automorphisms, more or less similar to the triangle, except they only permute those vertices. But the first one, well, the central one remains in place. Right? It is a fixed point of any automorphism of the star. Now, if I count the number of homomorphisms, right? Any homomorphism that maps anything here, I can use the same logic, right? If maps something here, then if I apply this one, well, it comes in triples. So if, what is going on? Yeah, it's somehow automatic. It wasn't automatic before, but modular counting is. Well, I can override it, so it's unfair competition. Okay, right. So anyway, if I map anything here, well, it contributes 0 into the total count because, well, I can repeat it 3 times, right? But if everything is mapped into the central point, that doesn't, well, this thing doesn't work for that. So what does it mean? This means that I have a relational structure graph, whatever. This modular counting problem is equivalent in a very strong sense. It has the same answer as the CSP of H. Well, I will denote it like H pi, where pi is the subgraph or substructure, which is obtained by restricting the original graph to the set of fixed points of my automorphism, like to here, right? So counting homomorphisms to graphs to a 3-star may be difficult, exact number, but because of that, well, the counting modulo 3 is trivial. I just need to map everything into the central point, and this is the only thing I can. Well, of course, I can repeat this process multiple times, right? I start with H, find an automorphism of order P, just take the fixed points. Then maybe in what I obtain, I again have a homomorphism of order P. I can restrict again and again and again. And eventually I will arrive to a structure which has no automorphisms of order P, so-called P-rigid structure. Okay, then I cannot play this game anymore and I have to do real work, finally. Okay, so if you do real work and compare the difficulty of exact counting with that, then you get the following. Well, that's a theorem by myself and my student Amir Hossein Kazeminian. Well, fairly recent one. So now, well, this problem where H is a graph, it's polynomial time if and only if okay, if and only if this P-rigid structure is easy for exact counting. That is, it's one of the two, anyway. Okay? And in all other cases, it's difficult. So that is a pretty difficult result, actually. So it's not trivial at all. So you somehow need to do this modular stuff in this case. Okay. That's the reference. It's still in the process. Good. So I probably should stop about here. So we have, in the case of general structures like knot graphs, things are a lot more difficult. Well, there are all kinds of, say, rigidity is not enough. You need to do more than that. Well, there are some properties like automorphisms of products of relational structures that work for graphs. They don't work for general structures. Well, we still can do a little bit. Say we can do parity in some, compute the parity in some cases. Also, it's going to be a little bit more difficult. Well, we can find other kinds of automorphism, like reductions. What else can we do? We can classify the complexity for 3-element structures, which is kind of pathetic, right? It's just 3-element structures. Well, and also some other other cases. In this case, it's just a massive case analysis, and so on. Okay. So, well, the last difficulty, well, actually, one of the obstacles in this path is a computing partition functions over finite sets, over finite fields. In this case, since the problem is that unbalanced relations that were hard in the exact counting are not necessarily so hard in this case, because there are all these cancellations and so on. So what we need to do, we need to look at spectral properties, like all these not yet, at eigenvalues of our adjacency matrix, of the matrix, use some Galois theory. It's still ongoing work, and many things are open. Okay, that's all I have to say. Thank you very much.
Thank you very much for the excellent talk. Does anybody have questions? I have a question about the complexity of the counting. So for a hard problem that you cannot do it in the polynomial time, so is there a method to modify the problem a little that we can, like approximation?
Yeah, so sometimes you can approximate. So in the case of homomorphisms, it rarely helps. But say in the case of partition functions, yes, there are cases when it's difficult to count exactly, but easy to approximate. There are several methods. Some of them are kind of very interesting, all this decay of correlations, or say you can represent your partition functions as a complex function and then look at the singularities and whatever. So there are kind of very strange and interesting methods in that case. Another approach is to look at so-called easy exponential algorithms. When, say, if you just have two graphs, you want to count the number of homomorphisms. The brute force, right? Just enumerating all mappings and looking at which of them is a homomorphism is the size of the target graph to the power of the original graph, right? But now the question is it possible, or when it is possible, to actually solve the problem not in the size of this graph to the power of this graph, but say some fixed number like 1.5 to the power of this graph. Right? So, for instance, if you look at coloring, right? If you look at coloring, then I say, okay, given the graph, is it k colorable? Where k is a part of the input. Then what you need to do, well, you need to go over all possible labelings, all possible colorings, and check which one are proper. But if you do it in a slightly more smart way, right, you can actually prove that in this case, you can do it in 3, not k to the power of the input graph, but 3 to the power of the input graph. It's a very simple dynamic programming algorithm. If you do it a little bit more, even more smarter, you can do it like 2 to the power of the input graph. So that kind of speeds up a lot. So that's another approach.
Thank you very much.
Thank you for the talk. I have a quick question about like modular counting. You've mentioned that for approximate counting, there are like some motivations from about. But for modular counting, is there easy to explain
When you may want something like this. Well, it is interesting exactly for computations in finite fields. Like, for instance, all sorts of cryptographic stuff and so on. Well, if you're just interested in complexity, I don't think there are kind of a clear practical application. So it's more like theoretical interest to understand how things work in this case.
Okay, thank you.
Any more questions? Okay, so if there's no more questions, let's thank the speaker again.